A supernova unleashes more energy in seconds than our Sun will in its entire lifetime. That is just a whisper from the universe's most extreme environments, places where the normal rules of reality break down completely. Today we are going on a tour of cosmic hostility, exploring 25 facts about worlds where oceans boil under alien skies, mountains are made of diamond, and storms rage for centuries. You will walk away with a profound understanding of just how strange, violent, and beautiful our cosmos truly is. We will see planets torn from their stars to wander eternal darkness and confront forces that can rip space and time apart. What single idea about our universe fills you with the most wonder? Our first stop lies 40 light-years from Earth, a world named Gliese 1214b. This exoplanet is a super-Earth, a planet with a mass several times greater than our own, but it is utterly alien in every other way. Astronomers believe its entire surface is a single, uninterrupted global ocean, but this is no serene, blue expanse. The atmosphere here is a thick, steamy blanket hundreds of times denser than Earth's, creating a pressure cooker of unimaginable intensity. The heat from its nearby star pushes the ocean's temperature to hundreds of degrees. Under these conditions, water does not simply boil away. It enters a bizarre fourth state of matter known as a supercritical fluid. Imagine a substance that is neither a true liquid nor a true gas, but a seething, corrosive broth with the properties of both. This is the ocean of Gliese 1214b. It has no surface as we know it, no distinct line between sea and sky, just a gradual thickening of a hot, dense fog into a churning, superheated abyss. This environment completely shatters our earthly definition of an ocean. It is a realm where the very idea of chemistry is rewritten, where molecules might interact in strange, pressurized ways we can barely simulate in a lab. Could any form of matter, any hint of a process we might recognize as a precursor to life, persist in such a cauldron? The possibility seems remote, yet this world stands as a stark testament to the universe's boundless capacity for creating environments of profound and hostile beauty. While that alien ocean redefines the word sea, our own solar system holds worlds where the sky itself performs a kind of alchemy. The ice giants Neptune and Uranus are realms of unimaginable pressure, and deep within their swirling blue atmospheres, a truly bizarre form of precipitation is thought to occur. Scientists believe it literally rains diamonds. The recipe begins with simple ingredients. The upper atmospheres of these planets contain vast amounts of methane, a simple molecule of carbon and hydrogen. As powerful storm systems churn, they can drag this methane down into the crushing depths. Here, pressures become millions of times greater than anything on Earth's surface, and temperatures soar to thousands of degrees. Under these hellish conditions, the bonds holding the methane molecules together are shattered. The hydrogen is stripped away, and the leftover carbon atoms are squeezed together with such immense force that they crystallize, forming tiny diamonds. These diamond particles, heavier than the surrounding slush of icy materials, then begin a long, slow fall through the planetary interior, a glittering hail descending toward the core. This is not just a poetic idea. Laboratory experiments here on Earth have recreated these extreme conditions using powerful lasers to blast plastic, which contains similar carbon and hydrogen, and observing the formation of nanodiamonds in the resulting shock waves. The models suggest this diamond rain could be a constant phenomenon, creating a steady drizzle of precious stones over geologic time. It leads to a staggering possibility. Some planetary scientists theorize that these ice giants may harbor solid cores encrusted with layers of diamond, or even vast subsurface oceans of liquid carbon with diamond icebergs floating within. Picture that for a moment, a planet's heart not of molten iron but of crystallized carbon forged in an eternal, crushing storm. It is a reminder that the universe's extremes are not just about destruction, but about transformation, turning the most common elements into treasures under forces we can scarcely comprehend. That diamond rain falls in a relatively stable, if violent, sky, but some stars are not afforded even that basic stability. They are cosmic projectiles flung from their homes at speeds that defy comprehension. These are hypervelocity stars, and one of the most famous, known as S5HVS1, is racing away from the heart of our Milky Way at an astonishing 1.6 million miles per hour. To grasp that speed, imagine a journey from Earth to the Moon in under 15 minutes. This star is not drifting, it is fleeing. The most likely culprit for this violent ejection is the supermassive black hole that lurks at our galaxy's center, Sagittarius A star. Picture a binary star system, two stars orbiting each other, wandering too close to this gravitational monster. The black hole's immense pull can capture one star, binding it into a tight, doomed orbit. In a process akin to a cosmic slingshot, the tremendous gravitational energy of that capture is transferred to the other star, which is then hurled outward at a fraction of the speed of light. It is a brutal trade, one star sacrificed to oblivion so that its partner might gain a ticket to eternity. Now untethered, this hypervelocity star embarks on a profoundly lonely voyage. It screams through the relative emptiness of intergalactic space, a place so vast and dark that the nearest galaxy might be millions of light years away. Its fate is a cold and dark one. It will never find another stellar system to call home. It will burn through its nuclear fuel on this solitary sprint, eventually cooling into a faint, dark ember that will continue its endless trajectory through the void between galaxies. It becomes a permanent exile, a ghost of a star carrying the violent signature of its birthright forever in its motion. An exile star is not the only kind of cosmic orphan. Far more common are the worlds that have been cast out, planets torn from their solar systems and set adrift in the infinite night. These are rogue planets, and their existence is a testament to cosmic violence on a planetary scale. The process often begins in the chaotic early days of a star system, when gravitational interactions between young, massive planets can be catastrophic. One world might be flung inward, consumed by its star, while another is ejected outward at tremendous speed, breaking free of its star's gravity entirely. It is set on a new, solitary course through the galaxy. The surface of such a world is a portrait of absolute desolation. With no sun to warm it, its temperature plummets toward the coldest possible limit in the universe, absolute zero. The very atmosphere, if it had one, would freeze solid and collapse onto the ground in a blanket of ice and snow. The landscape would be a frozen, airless wasteland, darker than the darkest night on Earth, illuminated only by the faint, cold light of distant, unmoving stars. There would be no dawn, no day, no year, only an eternal and unchanging midnight. Yet within this frozen tomb, a flicker of possibility might persist. Many of these rogue planets, especially the larger ones similar to gas giants, could retain immense internal heat from their violent formation. This geothermal warmth, trapped beneath a crust of ice many miles thick, could be enough to maintain vast global subsurface oceans of liquid water. Picture it, a world encased in a perpetual rocky ice shell as hard as steel, but beneath it a dark, warm sea, utterly isolated from the universe above. In that profound darkness, warmed only by the planet's own heart and perhaps by tidal forces from any large moons that were ejected alongside it, the basic conditions for chemistry, even for life as we understand it, could theoretically exist. It is a haunting thought. The most isolated, sunless place imaginable could, against all odds, cradle a hidden ocean, a secret pocket of warmth in the interstellar void. The sky from that hidden ocean's hypothetical shore would be the ultimate expression of loneliness, a starfield that never changes, a permanent reminder that home is nowhere to be found. The profound isolation of a rogue planet stands in stark contrast to a world gripped by a permanent, planet-wide storm. Venus presents a climate of such violence and strangeness it defies simple explanation. While its surface rotates at a glacial pace, taking 243 Earth days to complete a single spin, the upper atmosphere is caught in a screaming tempest. Winds at the cloud tops whip around the planet at over 200 miles per hour, completing a full circuit of Venus in just 4 Earth days. This phenomenon is called atmospheric superrotation, and it creates a permanent hurricane-force vortex that encircles the entire globe. The driving force behind this perpetual hurricane is a mystery scientists are still unraveling. It is believed to be powered by the intense heat from the sun, which Venus absorbs in enormous quantities due to its thick carbon dioxide atmosphere. This solar heating, combined with the planet's slow rotation, seems to create a colossal thermal tide, a wave of atmospheric pressure that pushes the upper clouds forward with relentless fury. Adding to the strangeness are the bizarre cloud patterns observed by space probes. The thick sulfuric acid clouds are not featureless, but often form into a giant, dark Y shape that stretches across the planet's face, a pattern that seems to be fixed in the super-rotating winds. This suggests a standing wave, a persistent atmospheric disturbance locked in place by the planet's topography or rotation, all while being carried along at hurricane speed. The result is a climate system of terrifying power. At the surface, the pressure is 92 times that of Earth, hot enough to melt lead and shrouded in a dim, reddish gloom. Above, the sky itself is a raging, global river of acid and wind, a permanent storm without end. It is a world where the very air is a faster, more violent entity than the ground beneath it. The permanent hurricane in its sky is only the beginning of Venus's horror. To stand on its surface is to experience a vision of hell made real. The temperature there is a constant 870 degrees Fahrenheit, hot enough to not just melt lead, but to keep it in a shimmering, liquid state. The atmospheric pressure bearing down is equivalent to being nearly 3,000 feet deep in Earth's ocean, a crushing 92 times heavier than the air we breathe. And that air itself is a toxic, corrosive stew, composed almost entirely of carbon dioxide, with clouds of sulfuric acid drifting high above a landscape bathed in a dim, eerie, reddish light. This combination creates an environment so hostile it has destroyed every spacecraft daring enough to touch down within minutes. The Soviet Venera landers of the 1970s and 80s were triumphs of engineering, armored like deep-sea submarines to withstand the immense pressure and heat. Yet even these robust probes succumbed quickly, their electronics frying and their structures corroding, typically lasting no more than 2 hours before falling silent forever. They transmitted back our only fleeting glimpses of a rocky desert scattered with slab-like stones under that perpetual orange gloom. What geological secrets does that oppressive shroud hide? Radar maps from orbiting spacecraft have revealed vast highland regions called tesserae, complex, fractured terrain that looks like a giant's crumpled tile floor. This tessera terrain suggests a history of intense tectonic activity, perhaps the remnants of ancient continents that moved and buckled under forces we do not yet understand. Some scientists even speculate that Venus may have had a much more Earth-like climate in the distant past, with liquid water oceans, before a runaway greenhouse effect boiled them away and transformed the planet into the pressure cooker it is today. The surface of Venus, therefore, is not just an extreme environment, it is a catastrophic warning, a possible future for any world that loses control of its climate, forever hidden beneath clouds of acid and a sky of fire. If Venus is a vision of hell, then the outer solar system offers a different kind of fury, one sculpted not by fire but by ice. Here, volcanoes do not spew molten rock. They erupt with frozen water, ammonia, or even nitrogen slush in a process called cryovolcanism. On the small, brilliant moon Enceladus orbiting Saturn, this creates one of the solar system's most breathtaking sights. Enceladus is a world of pure white ice, cracked and scarred at its south pole by a series of deep fissures known as tiger stripes. From these gashes, enormous geysers blast hundreds of miles into space, a continuous eruption of water vapor, ice particles, and simple organic molecules. This material forms a faint ring around Saturn itself, a celestial signature of the Moon's inner turmoil. The force behind these eruptions is not internal heat from radioactive decay, as on Earth, but the relentless gravitational tug of war between Enceladus and its giant planet. Saturn's immense gravity flexes and squeezes the Moon's interior, generating friction and heat through tidal forces. This heat is enough to maintain a vast, global ocean of liquid water trapped between the Moon's icy shell and its rocky core. The plumes we see are essentially that buried ocean venting directly into space, a cosmic sample return mission happening naturally. When the Cassini spacecraft flew through these plumes, it tasted their composition, confirming the presence of salts and complex carbon-based compounds, the very ingredients and energy sources thought necessary for life. Enceladus, therefore, is not just an icy world. It is a geologically active water world with a subsurface sea in direct contact with a warm, mineral-rich seabed. It presents a profound possibility. In the absolute darkness beneath that ice shell, around hydrothermal vents on an alien ocean floor, could chemistry have given rise to biology? This tiny, frozen moon has become one of the top candidates in our entire search for extraterrestrial life, a hidden ocean screaming its existence into the void through jets of ice. That hidden ocean on Enceladus whispers of subtle, internal forces. But around Jupiter, the solar system's giant, the violence is external and spectacularly loud. Jupiter is not just a planet, it is a magnetic monster. Its magnetosphere, the immense bubble of magnetic influence carved out by the planet's furious rotation and liquid metallic hydrogen core, is the single largest structure in our solar system. If it were visible in our night sky, it would appear larger than the full moon, a vast, invisible shield stretching over 5 million miles toward the Sun and tapering into a comet-like tail that reaches beyond the orbit of Saturn. This magnetic domain is so colossal it could comfortably envelop the Sun itself with room to spare. Within this invisible fortress, Jupiter operates a natural particle accelerator of terrifying power. The planet's intense magnetic field captures charged particles, mostly electrons and protons, whipping them to nearly the speed of light. These form the lethal radiation belts that surround Jupiter, zones so flooded with energetic radiation they can fry the electronics of an unshielded spacecraft in mere hours. Probes like Galileo and Juno had to be armored with special radiation-hardened vaults just to survive their missions. This radiation is a constant, invisible hurricane of atomic shrapnel, a testament to the raw energetic fury contained within Jupiter's magnetic grip. Yet, this destructive power also creates one of the universe's most beautiful displays. At the planet's poles, these trapped particles are funneled down magnetic field lines and slam into the upper atmosphere, igniting permanent, planet-sized auroras. These are not the shimmering green curtains of Earth. Jupiter's auroras are ultraviolet infernos, rings of brilliant light larger than our entire planet, and they are not powered by the solar wind alone. Their primary fuel comes from an unexpected source, the tortured moon Io. Io, the most volcanically active world in the solar system, spews over 1 ton of sulfur and oxygen gas every second from its countless volcanoes. This material becomes ionized, caught in Jupiter's magnetic grip, and forms a vast donut-shaped ring of plasma around the planet. As Jupiter rotates, this torus of charged gas sweeps through the magnetic field, generating a current of 5 million amps that flows directly into the polar regions, supercharging the auroras with volcanic fury. So the stunning lights at Jupiter's poles are a direct beacon, a luminous signal of the complex and violent gravitational dance between a giant planet and its volcanic moon. It is a planet-sized circuit forever closed, powered by orbital mechanics and erupting into a perpetual electromagnetic storm. Io is a world on fire, a permanent volcanic apocalypse. This mottled yellow moon of Jupiter holds the undisputed title of the most volcanically active body in our solar system. Its surface is a chaotic canvas painted in sulfur, with over 400 active volcanoes constantly spewing plumes of gas and molten rock hundreds of miles into the thin sky. Some of these are not simple cones, but vast, simmering calderas, depressions filled with churning lava. The most famous is Loki Patera, a lava lake so immense it could swallow the entire city of Los Angeles. This is not a still pool, but a roiling, overturning sea of molten rock, its crust periodically collapsing in epic waves of incandescent heat. The energy required to power this global furnace does not come from radioactive decay in a core as on Earth. Instead, Io is baked from the inside out by the relentless gravitational tug of Jupiter and its neighboring large moons, Europa and Ganymede. As Io orbits, these competing gravitational forces stretch and squeeze the moon's interior, a process called tidal heating. This constant internal friction generates immense heat, melting rock into magma that forces its way to the surface in a never-ending eruption. The result is a landscape in perpetual, violent renewal. Lava flows, some hundreds of miles long, constantly repave the surface, while volcanic vents coat everything in frosts of yellow sulfur and white sulfur dioxide snow. Mountains taller than Everest are thrust upward, only to be buried or torn down by new geologic forces within a million years, a blink in cosmic time. Io is a world without rest, a testament to the transformative power of orbital mechanics, where gravity itself becomes the stoker for a planetary-scale forge. While Io's volcanoes burn with molten rock, Saturn's largest moon, Titan, presents a world shaped by a different kind of fluid. Titan is the only place beyond Earth with a confirmed, active hydrologic cycle, a system of evaporation, clouds, rain, and flowing liquid that carves its landscape. But here, the liquid is not water. It is liquid methane and ethane, hydrocarbons that exist as gases here on our warm planet. On Titan's frigid surface, where temperatures hover around -290 degrees Fahrenheit, these compounds behave just like water does on Earth. They pool into vast lakes and seas, they flow in rivers that carve valleys through icy bedrock, and they evaporate to form thick, orange clouds in a dense nitrogen atmosphere. The Cassini spacecraft and its Huygens lander gave us our first intimate look at this alien world. Huygens descended through that hazy orange sky in 2005, transmitting images of a landscape that looked hauntingly familiar, a plain of rounded ice pebbles smoothed by what must have been flowing liquid. From orbit, Cassini's radar pierced the opaque atmosphere to map Titan's surface, revealing dark, smooth expanses near the poles that could only be bodies of liquid. The largest of these, Kraken Mare, is a sea of methane and ethane larger than Earth's Caspian Sea. It has coastlines, islands, and even tides driven by Saturn's gravity. Rivers of liquid hydrocarbons snake across the terrain, draining into these seas, their channels etched into water ice as hard as rock. This discovery transforms Titan from a distant moon into a dynamic world, a place with weather, geology, and even the potential for chemistry we are only beginning to understand. In Titan's cold rivers and seas, the ingredients for life as we know it do not exist. But scientists speculate that a different kind of probiotic chemistry could be at work, one based on the complex interplay of methane, ethane, and nitrogen under the influence of solar radiation. Could the building blocks of a truly alien biology, one that breathes hydrogen and uses liquid methane as its solvent, be forming in those dark, oily depths? Titan stands as a profound lesson in cosmic versatility, proving that the processes that shape a living world can operate with entirely different materials, creating a mirror of Earth that is both deeply familiar and utterly alien. Amidst the flowing methane rivers and icy plains of Titan, another of Saturn's wonders defies all earthly logic. At the planet's north pole, a structure of such geometric perfection exists it looks engineered. This is Saturn's north polar hexagon, a six-sided jet stream wider than two Earths placed side by side, and it has persisted for at least 4 decades. Imagine a honeycomb cell drawn on a planetary scale, its walls composed of howling winds that race at over 200 miles per hour. This is not a static shape etched into clouds, but a roaring river of atmospheric gas, a highway of wind tracing an impossible polygon around the pole. At its very center sits another marvel, a colossal hurricane. This storm's eye is about 50 times larger than the average hurricane eye on Earth, a vast, calm vortex ringed by towering clouds. The entire hexagonal structure rotates with a period that matches Saturn's deep interior rotation rate, a clue that it is anchored to the planet itself, not just a fleeting weather pattern. How does such a precise shape form in a turbulent, gaseous atmosphere? The leading theory involves the physics of standing waves. If you vibrate a fluid, certain stable patterns can emerge. In a fast-rotating planet like Saturn, the atmosphere may behave like a fluid in a spinning ball, and the interaction between different layers and speeds could set up a stable wave pattern with 6 peaks and 6 troughs. This pattern then guides the jet stream, painting a hexagon in the sky with wind. Its astonishing stability, observed by Voyager in the 1980s and still present when Cassini arrived decades later, suggests it is a fundamental feature of Saturn's atmospheric mechanics. It is a natural sculpture of fluid dynamics, a permanent testament to the hidden order that can arise from chaos, a geometric storm locked in an endless, precise dance around a planet's crown. That geometric storm is a masterpiece of planetary physics, yet it pales in comparison to the raw, paradoxical fury of our own star. The Sun presents one of the most enduring mysteries in all of astrophysics, a puzzle of heat that defies basic logic. The Sun's visible surface, the photosphere, glows at a searing 5,500 degrees Celsius. Yet, just above this apparent boundary, in the wispy outer atmosphere called the corona, the temperature skyrockets to between 1 and 3 million degrees. It is as if you walked away from a roaring campfire and suddenly found yourself inside a blast furnace. This coronal heating problem has baffled scientists for decades. How can the atmosphere be hundreds of times hotter than the surface it emanates from? The leading suspect is the Sun's own magnetic field. Our star is not a placid ball of gas, it is a tangled, dynamic knot of magnetic forces. These fields are constantly braiding, snapping, and reconnecting in a process aptly called magnetic reconnection. Think of it like rubber bands being twisted together until they suddenly break, releasing a tremendous burst of energy. On the Sun, when magnetic field lines cross and reconfigure, they convert magnetic energy directly into heat and kinetic energy, explosively accelerating particles to incredible speeds. Another theory points to nanoflares, tiny, ubiquitous explosions happening across the solar surface. Individually, they are too small to detect, but collectively, billions of these microexplosions could be the steady furnace that superheats the corona. We see the breathtaking effect of this million-degree atmosphere during a total solar eclipse. When the moon perfectly blocks the brilliant photosphere, the ghostly white corona emerges, a delicate, structured halo of plasma stretching millions of miles into space. That beautiful, shimmering light is the glow of unimaginable heat, a visual testament to a fundamental cosmic mystery still simmering at the heart of our solar system. The Sun's magnetic fury is a local phenomenon, a mere whisper compared to the cosmic roar emanating from the hearts of distant galaxies. Here, we find the universe's most powerful persistent engines, driven by supermassive black holes that have transformed themselves into celestial monsters. These are not the quiet, dormant giants like the one at our galaxy's center. These are active galactic nuclei, and their power source is a spectacle of pure, unadulterated violence. As vast amounts of gas, dust, and even entire stars spiral into the black hole's gravitational grip, they form a swirling, superheated disk of plasma known as an accretion disk. Temperatures here reach millions of degrees, glowing with an intense radiation that can outshine every star in its host galaxy combined. But the true signature of these beasts is not what goes in, but what is launched out. From the poles of this chaotic system, perpendicular to the disk, twin beams of matter are catapulted into intergalactic space. These are relativistic jets, narrow, focused torrents of ionized gas and magnetic fields that are accelerated to velocities so close to the speed of light that the laws of relativity dramatically warp their behavior. The energy required for this is incomprehensible, a significant fraction of the rest mass energy of the infalling matter being converted directly into kinetic fury. These jets are not gentle streams, they are scalpel-sharp, piercing through their host galaxy and extending for tens or even hundreds of thousands of light-years into the void. That means a single jet can stretch a distance greater than the entire breadth of the Milky Way. As they slam into the tenuous gas that exists between galaxies, they create colossal, glowing shockwaves, radio lobes that can be seen across the cosmos. When one of these jets is pointed almost directly at Earth, we see the most luminous object in the universe, a quasar. A single quasar can be 1,000 times brighter than our entire galaxy, a beacon visible from the edge of the observable universe powered by a black hole's feast. These jets are more than just spectacular light shows. They are galactic-scale regulators, pumping enormous energy into their surroundings. They can heat intergalactic gas, preventing it from cooling and forming new stars, effectively sterilizing a galaxy of future stellar birth. They can also trigger star formation in other regions by compressing clouds of gas with their immense shockwaves. The relativistic jet is the ultimate cosmic feedback mechanism, a black hole's way of shaping its own galaxy, and perhaps the entire cosmic web, with beams of energy fired at nearly the speed of light. Relativistic jets are a sustained, focused scream of power, but the universe also delivers its energy in sudden, blinding flashes of pure annihilation. These are gamma-ray bursts, the single most energetic events known to exist since the Big Bang itself. In a span of seconds, a gamma-ray burst can release more energy than our Sun will emit across its entire 10 billion-year lifetime. For that fleeting moment, it outshines every star in its host galaxy, a cosmic flashbulb that briefly drowns out all other light. The source of this apocalyptic fury is typically one of two catastrophic stellar deaths. The long-duration bursts, lasting more than 2 seconds, are thought to be the birth cries of black holes, created when the core of a truly massive star, many times heavier than our Sun, collapses under its own weight. As the star's outer layers plummet inward, they form jets of ultra-relativistic particles that drill through the collapsing star and blast out into space at 99.99% the speed of light. The shorter bursts, lasting less than 2 seconds, are believed to be the final, violent merger of two neutron stars, or a neutron star and a black hole, a collision that also forges focused beams of unimaginable energy. We do not see the explosion itself, we only see the narrow beam of gamma rays, the highest energy form of light, if that beam happens to be pointed directly at Earth. It is like staring down the barrel of a cosmic cannon at the exact moment it fires. The afterglow of such an event can linger for days or weeks across other wavelengths, a fading echo of the catastrophe. The implications are sobering. If a gamma-ray burst were to occur within a few thousand light-years of Earth and its jet were aimed at us, the effects would be planetary in scale. The initial blast of gamma rays would strip away our protective ozone layer in an instant. The subsequent interaction with the atmosphere would create a blanket of nitrogen oxides, triggering global acid rain and plunging the planet into a prolonged, deep freeze by blocking sunlight. Many scientists point to a mass extinction event around 450 million years ago, the Ordovician extinction as a possible candidate for such a gamma-ray burst strike. These bursts are random, unpredictable, and utterly indifferent. They serve as the ultimate reminder that the cosmos is not just a place of beauty, but also of sudden, sterilizing violence, capable of resetting the biological clock of a planet from halfway across the galaxy. A gamma-ray burst is the universe's most violent shout, but the object left behind in the wake of its creation is a monument to silence and density beyond comprehension. This is the neutron star, the collapsed core of a giant star that exploded but was not quite massive enough to form a black hole. What remains is a city-sized sphere of the most extreme matter in existence. During the supernova, the star's outer layers are blasted into space while its core, under unimaginable gravitational pressure, collapses inward. Protons and electrons are crushed together, forced to merge into neutrons. The result is a star composed almost entirely of these subatomic particles, packed together with no empty space. The density is simply unfathomable. A single sugar cube of neutron star material would weigh about 100 million tons on Earth, as much as a mountain. That means a teaspoon of this stuff contains more mass than every single person alive today combined. The entire star, typically only about 12 miles across, contains 1.5 times the mass of our Sun, which is over 860,000 miles in diameter. It is matter squeezed to its absolute limit. The surface of a neutron star is not gaseous or molten, but solid. It forms a crystalline crust, an iron lattice harder than diamond, thought to be perhaps 10 billion times stronger than steel. This crust floats atop an inner ocean of superfluid neutrons, a frictionless quantum liquid that can flow without any viscosity. The star's gravity is correspondingly monstrous. On its surface, gravity is about 100 billion times stronger than Earth's. Any object approaching would be subjected to a process called spaghettification. The pull on the side closest to the star would be so much stronger than the pull on the far side that the object would be stretched into a long, thin strand of atoms before being shredded into a stream of particles. But perhaps the most terrifying variant of this stellar corpse is the magnetar. When a neutron star forms with an exceptionally rapid spin, its already intense magnetic field can be amplified to ludicrous levels. A magnetar's magnetic field is about 1,000 trillion times stronger than Earth's. If a magnetar were located halfway between Earth and the Moon, its magnetic field would erase the data from every credit card on our planet. These fields are so powerful they can literally twist the star's solid crust, causing starquakes that release colossal bursts of gamma rays and X-rays, briefly outshining entire galaxies. The neutron star is a universe in miniature, a place where the rules of quantum physics and gravity collide to create a perfect, dense, and violently magnetic sphere. That magnetic field is not merely a static force, it is a weapon of cosmic destruction. When a magnetar's unimaginably powerful magnetic field evolves, it exerts a stress on the star's own crust, that 10-mile thick shell of iron harder than diamond. This stress builds and builds until the crust can no longer hold. It fractures. This is a starquake, a seismic event on a stellar scale. The energy released in that single crack is staggering, equivalent to a magnitude 32 earthquake. To put that in perspective, the most powerful earthquake ever recorded on Earth released roughly the energy of 32 billion Hiroshima bombs. A magnetar starquake releases over 100 billion times more energy than that. This cataclysm is not felt as shaking, but seen as a blinding flash of radiation. The rupture unleashes a torrent of gamma rays and X-rays, a pulse of pure energy that can, for a fraction of a second, outshine every star in the Milky Way galaxy combined. On December 27, 2004, our planet was brushed by the dying scream of such an event. A magnetar named SGR 1800-620, located 50,000 light-years away in the constellation Sagittarius, unleashed a starquake. For 0.2 of a second, its gamma-ray flash was brighter than the full moon, even at its immense distance. The pulse of energy was so intense it actually affected Earth's upper atmosphere. It ionized atoms in our ionosphere, causing it to suddenly swell and distort, an effect normally caused by powerful solar flares from our own nearby sun. This event, detected by satellites and even by radio telescopes that sensed the atmospheric disturbance, delivered a humbling message. An explosion on a tiny, city-sized object halfway across our galaxy was powerful enough to physically reach out and touch our planet's sky. It forces us to ask what would happen if such a magnetar were closer, say within 10 light years. The resulting gamma-ray blast could strip our ozone layer, triggering a global extinction event. The magnetar reminds us that true cosmic power is not always about vast size, but about unimaginable density and magnetic fury contained within a perfect, trembling sphere. That magnetic fury is contained within a searing, dense star, but the universe holds the opposite extreme in an equally delicate form. Drifting through the darkness 5,000 light-years from Earth is a cosmic ghost known as the Boomerang Nebula, and it holds the title of the coldest natural place we have ever found. Measurements from telescopes like the Atacama Large Millimeter Array show its temperature is a mere 1 degree above absolute zero, the theoretical limit where all molecular motion stops. That is just 1 single degree warmer than -459.67 degrees Fahrenheit, colder than the faint, uniform glow of the Big Bang that permeates all of space. This profound chill is the work of a dying star. The Boomerang is a protoplanetary nebula, a brief phase in a star's life when it has exhausted its fuel and is shedding its outer layers, but its core is not yet hot enough to ionize the gas into a bright planetary nebula. What makes this star special is the phenomenal speed at which it is expelling this material. The gas is streaming outward at over 300,000 miles per hour, a supersonic wind moving faster than a bullet. This rapid expansion is the key to the deep freeze. In the same way a refrigerator cools by letting compressed gas expand rapidly, the nebula's furious outflow causes its own gases to expand and cool to this record-low temperature. The result is a hauntingly beautiful structure. We see 2 nearly symmetric lobes of cold gas and dust stretching outward, giving it a bow tie or boomerang appearance from our vantage point. This frigid cloud is actively absorbing the energy from the cosmic microwave background, the leftover heat from the birth of the universe, making it even colder than the empty space around it. It stands as a stunning counterpoint to the million-degree coronas of stars and the searing accretion disks of black holes. Within a single galaxy, we find environments separated by a thermal chasm of over 1 million degrees, from the cold, quiet death of a sun-like star to the violent, magnetic rebirth of a stellar corpse. Even the coldest nebula is born from a star's final breath, but some stars do not wait for death to begin shedding their skin. They are cosmic giants in a state of perpetual, violent eruption. These are the hypergiant stars, and their stellar winds are hurricanes of matter on an unimaginable scale. Take VY Canis Majoris, a star so colossal it would engulf the orbit of Jupiter if placed at the center of our solar system. This behemoth is not stable. Its immense gravity struggles to hold onto its own outer layers, and the fierce radiation pressure from within pushes them away. The result is a supersonic wind of gas and dust blasting outward from the star's surface at speeds of hundreds of thousands of miles per hour. The scale of this loss is incomprehensible. Every single year, VY Canis Majoris blows off an amount of material equivalent to 30 times the mass of our entire planet Earth. That means in the span of a human lifetime, this one star casually ejects more mass than exists in all the planets, moons, and asteroids of our solar system combined. This is not a gentle breeze. It is a continuous, titanic exhalation that sculpts the space around it. The expelled material does not simply vanish. It piles up in vast, intricate structures, creating a nebula of its own making. For VY Canis Majoris, this is a chaotic, dusty shroud, but for other hypergiants, the artistry is more distinct. Eta Carinii, another monstrous star system, underwent a colossal eruption in the 1840s, briefly becoming the second brightest star in the night sky. That event, known as the Great Eruption, ejected at least 10 times the mass of our Sun in a few short years. That material now forms the homunculus nebula, two vast, expanding lobes of gas and dust that resemble a cosmic hourglass, a beautiful tomb being built in real time. These winds and eruptions are the star's death throes played out over centuries. They signal a core that is burning through its nuclear fuel at a frantic, unsustainable rate. Every gust of this hypergiant wind is a countdown, a sign that the star is approaching its final, cataclysmic instability. When the end comes, it will be a supernova of staggering proportions, potentially a hypernova that could unleash a gamma-ray burst. The nebula we see around it today, that beautiful, complex structure, will be the first layer of debris blasted by the final, definitive explosion. These stars live their entire lives as slow-motion supernova, writing their epitaphs in stellar winds long before the final page is turned. The stellar winds of hypergiants sculpt vast, dusty shrouds, but between the threads of the universe's tapestry lie spaces of a different magnitude. These are the cosmic voids, the great deserts of intergalactic space. Imagine the most isolated place you can conceive, then expand that emptiness to a scale that dwarfs human comprehension. A cosmic void is a region of space, typically spanning 100 to 400 million light-years across, that contains almost no galaxies. It is not a perfect vacuum, as it holds the sparse gas and dark matter that permeates all of space, but it is devoid of the bright islands of stars that define the cosmic landscape. These voids are not random empty pockets. They are fundamental components of the universe's large-scale structure, which resembles a vast three-dimensional spiderweb known as the cosmic web. In this model, galaxies are not scattered like salt. They are concentrated along the dense filaments and knots of this web, where gravity has pulled matter together over billions of years. The voids are the immense, dark spaces between these threads. They are the negative space that defines the positive, the emptiness that gives the structure its form. For a hypothetical traveler within a void, the experience would be one of profound and terrifying isolation. The nearest major galaxy would be tens of millions of light-years away. Looking out from a spacecraft, the sky would appear almost perfectly black, punctuated by only a handful of faint, lonely dwarf galaxies. The brilliant tapestry of the Milky Way, with its thousands of visible stars, would be utterly absent. There would be no nearby stars to warm a planet, no nebulae to light the darkness, only the cold, uniform glow of the cosmic microwave background, the echo of the universe's birth. These voids are still dynamic. The subtle gravitational pull from the surrounding web of galaxies slowly drains them, causing the sparse gas within to flow outward toward the denser filaments. Over eons, this makes the voids even emptier while feeding the growth of the structures at their edges. They are not static holes, but actively evolving features, expanding as the universe itself expands. To contemplate a void is to confront the true meaning of emptiness, a volume so vast that light itself takes hundreds of millions of years to cross it, carrying no news of other worlds, only the silent testimony of space. That profound cosmic emptiness is a chilling thought, yet within our own solar system, a different kind of hostility awaits, one that is invisible and relentless. Jupiter's moon, Europa, is a world defined by contradiction. Beneath its cracked, icy shell lies a global ocean of liquid water, more than twice the volume of all Earth's oceans combined, making it one of the most promising places to search for life. But to reach that hidden sea, you would first have to survive its surface, and that is a deadly proposition. Europa orbits directly within the heart of Jupiter's ferocious radiation belts. Every square inch of its icy face is constantly bombarded by high-energy electrons and ions trapped in the giant planet's magnetic field. this isn't a gentle drizzle. It is a torrential downpour of atomic shrapnel, a radiation bath so intense it would deliver a lethal dose to a human in mere minutes, and it would fry the electronics of an unshielded spacecraft in days. This relentless bombardment has transformed Europa's surface ice. It breaks apart the water molecules, creating a host of reactive chemicals right there in the ice. You get oxygen, hydrogen peroxide, and various sulfur compounds, all forged by the ceaseless radiation. This creates a surface that is chemically toxic and hostile, a frozen desert sterilized by Jupiter's magnetic fury. Yet, this very process might be the key to unlocking life in the ocean below. The constant churning of Europa's icy crust, driven by the tidal flexing from Jupiter's gravity, acts like a giant, slow-moving conveyor belt. Surface ice, now packed with these radiation-created oxidants and chemicals, is thought to be gradually drawn downward over geologic time. It sinks through fractures and shifting ice plates, eventually mixing into the subsurface ocean. There, at the warm, rocky seafloor where hydrothermal vents might exist, these surface-borne oxidants could meet with minerals and reductants from the ocean floor. This combination is essentially a battery, a potential energy source for microbial life. The most hostile environment in the Jovian system, the radiation-blasted surface, could therefore be the very pantry that stocks the deep ocean with the chemical energy needed to sustain biology. Europa presents a stunning paradox. Its greatest threat from above may be the secret ingredient for life below, a system where the universe's destructive power is harnessed over millions of years to potentially fuel creation in the eternal dark. Europa's hidden ocean is a paradox of hostile chemistry and potential life, but some cosmic boundaries offer no such second chance. At the center of the galaxy Messier 87, 55 million light-years away, lies a gravitational monster so powerful it warps the fabric of reality itself. This is M87 star, a supermassive black hole with a mass of 6.5 billion suns, and in 2019 humanity captured its shadow. That now iconic image shows not the black hole itself, for no light can escape it, but its silhouette against a swirling maelstrom of superheated gas. The glowing orange ring is the accretion disk, a whirlpool of plasma moving at nearly the speed of light and heated to billions of degrees. At its center lies a perfect circle of darkness, the shadow of the event horizon. This is the ultimate point of no return, the boundary where the black hole's gravitational pull becomes so intense that not even light, the fastest thing in the universe, can break free. It is a one-way membrane in space and time. Cross it, and all paths lead inward to the singularity, a place where our known laws of physics break down completely. The event horizon is not a physical surface you could stand on. It is a mathematical limit, a threshold of cosmic inevitability. Yet, its effects on the space around it are profoundly physical. As you approach this boundary, time itself begins to warp in a phenomenon called gravitational time dilation. To a distant observer watching you fall, your clock would appear to tick slower and slower. You would seem to move in agonizing slow motion, your image reddening and fading as you approach the event horizon, freezing forever at the moment of crossing. From your own perspective, however, time would feel normal. You would cross the horizon in a finite moment, but once inside, the direction toward the black hole's center becomes your future. There is no stopping, no turning back. The forces at work are equally terrifying. The difference in gravity between your head and your feet, known as tidal forces, would stretch you into a long, thin strand of atoms in a process vividly named spaghettification. For a stellar mass black hole, this shredding would happen well outside the event horizon. But for a supermassive giant like M87 star, its immense size actually means its event horizon is far away from its central point of infinite density. You could theoretically cross the horizon of such a behemoth intact, only to be inevitably pulled and stretched toward the core later in a one-way journey to oblivion. The glowing ring in that first image is the last photon orbit, the point where light is bent so severely it circles the black hole like a cosmic racetrack before either falling in or escaping to our telescopes. That image, a dark pupil ringed with fire, is our most direct view of a place where the universe writes its most extreme rules, a silent testament to a darkness that consumes everything, even light itself. That event horizon marks a final boundary, but the energy released just outside it can illuminate the cosmos. A quasar is the universe's ultimate lighthouse, a beacon of such ferocious intensity that it can outshine every single star in its own galaxy combined. The engine for this cosmic brilliance is a supermassive black hole in a state of voracious, violent feasting. Unlike the quiet giant at our galaxy's center, the black hole at the heart of a quasar is surrounded by a vast, swirling accretion disk of gas, dust, and shredded stars. As this material spirals inward at nearly the speed of light, friction and tidal forces heat it to millions of degrees, causing it to glow with a blinding light across the electromagnetic spectrum. The sheer scale of this power is difficult to grasp. A single quasar can be 1,000 times more luminous than our entire Milky Way galaxy, yet this incredible light comes from a region not much larger than our solar system. It is an almost inconceivable concentration of energy. For decades after their discovery, quasars were mysterious, star-like points of radio energy. We now understand they are not stars at all, but the active, blazing cores of incredibly distant galaxies, their stellar populations completely washed out by the glare of their central monster. Their extreme distance means we are seeing them as they were billions of years ago, during a more chaotic and violent epoch of cosmic history. In the early universe, galaxies were richer in gas, and collisions between them were far more common. These collisions funneled vast reservoirs of fuel directly into the waiting supermassive black holes at their centers, igniting them into quasars. These beacons therefore serve as crucial signposts, illuminating the era when the first giant black holes were forming and growing, shaping the galaxies that would eventually become the stable spirals and ellipticals we see today. To observe a quasar is to look back in time to the universe's rambunctious youth, a time of colossal collisions and brilliant, hungry hearts at the center of creation. The brilliant fury of a quasar is a beacon across cosmic time, but our own solar system holds a frontier of profound darkness and cold. Far beyond the orbit of Neptune, beyond even the scattered disk of objects like Pluto, lies the Oort cloud. This is not a dense belt like the asteroid ring, but a vast, hypothetical spherical shell of icy remnants, a light year from the Sun at its outer edge. Picture a gargantuan bubble, its inner boundary starting perhaps 2,000 times farther from the Sun than Earth, and its outer edge extending halfway to the nearest star. Within this unimaginable volume drift trillions, perhaps even quadrillions of icy planetesimals, each a frozen relic from the solar system's violent birth 4.5 billion years ago. These are not compact rocks, but dirty snowballs of water ice, ammonia, methane, and dust, some as large as mountains, most no bigger than a city block. They are the icy sentinels of our solar system's outermost reach, orbiting in a perpetual, frozen twilight. The conditions here are the very definition of extreme. Sunlight is so feeble that the Sun itself would appear as nothing more than an exceptionally bright star, a pinpoint of light lost in the stellar background. Temperatures hover just a few degrees above absolute zero, a cold so deep that molecular motion nearly ceases. These objects exist in a state of suspended animation, preserved in the deep freeze of interstellar space. This ghostly cloud is not just a cosmic curiosity. It acts as a vast reservoir for the long-period comets that occasionally grace our skies. The gentle gravitational nudges from passing stars, or the tidal pull of the Milky Way galaxy itself, can dislodge one of these icy bodies from its tenuous orbit. Once disturbed, it begins a fall of tens of thousands of years inward toward the warmth of the Sun. As it approaches, the ices on its surface begin to vaporize, creating the spectacular glowing coma and tail that transform it from a dark iceberg into a celestial wanderer. The Oort cloud is therefore a cosmic archive and a delivery system. It is the frozen attic of our solar neighborhood, holding pristine material unchanged since the system's formation, and it occasionally sends a piece of that ancient history screaming into the inner planets on a long, slow orbit. To contemplate it is to understand that our sun's influence stretches far farther than the light of its planets, its gravitational whisper still holding sway over a sphere of darkness 1 light-year across, a final frontier of ice and memory. Within the silent aftermath of a supernova, a different kind of stellar corpse keeps time with a beat of unimaginable precision. These are pulsars, the lighthouses of the cosmos. When a neutron star is born with its magnetic poles misaligned from its axis of rotation, it becomes one of these cosmic metronomes. The star's intense magnetic field channels radiation into narrow, focused beams that shoot out from its magnetic poles like the beams from a lighthouse. As the star spins, these beams sweep across the universe. If one of those beams happens to cross Earth's line of sight, we detect a regular pulse of radio waves, or sometimes X-rays or gamma rays with each rotation. The consistency of this pulse is what makes pulsars truly extraordinary. They are nature's most perfect natural clocks. Some pulsars, known as millisecond pulsars, spin hundreds of times per second, and their rotational periods are stable to a level that rivals our best atomic clocks on Earth. This incredible precision allows astronomers to use them as tools for testing the laws of physics, like Einstein's theory of general relativity, and even for a futuristic concept called a pulsar navigation system for spacecraft. The discovery of the first pulsar is a story of delightful cosmic confusion. In 1967, a graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope when she noticed a strange, repeating signal. It pulsed with such perfect regularity every 1.337 seconds that she and her supervisor, Anthony Hewish, half-jokingly labeled it LGM1 for little green men. They genuinely considered the possibility it might be an artificial beacon from an extraterrestrial civilization. Of course, the truth was even more fascinating. They had discovered PSRB 1919+21, a rapidly spinning neutron star about 2,000 light-years away, its beam sweeping past our planet with the unwavering rhythm of a cosmic heart. That moment of discovery reminds us that the universe's most extreme objects often present themselves as mysteries first, their true nature hiding behind a mask of the seemingly impossible. Our final destination is the ultimate fate of stars like our own sun, a future written in crushing density and serene, terrible beauty. After a sun-like star exhausts its nuclear fuel, it does not explode in a supernova. Instead, it gently sheds its outer layers, creating a beautiful planetary nebula, a glowing shell of gas that will eventually disperse. What remains is the star's exposed core, a white dwarf. This stellar ember is a sphere of degenerate matter, a state where atoms are packed so tightly that their electron shells are completely smashed. A typical white dwarf packs a mass comparable to our Sun into a volume no larger than Earth. A single teaspoon of its material would weigh several tons here on our planet. This incredible density creates a surface gravity of staggering power, hundreds of thousands of times stronger than Earth. Any object, any asteroid or planetesimal that strays too close would be subjected to this immense force. It would be tidally shredded into dust, and that dust would then rain down onto the white dwarf's surface. Under that phenomenal gravity, the chemical elements in that debris do not stay separate. They are crushed and mixed, their distinct identities erased in a process called gravitational sedimentation. The heavier elements like carbon, oxygen, and iron sink, while the lightest, hydrogen and helium, float to the top. The result is a stellar atmosphere, often of surreal purity, a layer cake of elements sorted by their atomic weight under a force we can scarcely replicate. These white dwarfs become cosmic archivists, their atmospheres acting as forensic records. By analyzing the light from a white dwarf, astronomers can detect the spectral signatures of elements that should have sunk out of sight long ago. The presence of silicon, magnesium, or iron in its atmosphere is a telltale sign of a recent meal, evidence that the white dwarf has been consuming the remains of its own planetary system. We are literally seeing the ashes of obliterated worlds, asteroids, and perhaps even planets, their substance homogenized and laid bare on this incredible surface. They are the quiet, dense tombstones of solar systems, holding within their perfect gravitational grip the final, elemental record of all that once orbited them. From diamond rains on distant ice giants to the screaming jets of supermassive black holes, the universe is a gallery of impossible violence and beauty. We have walked on worlds where oceans are corrosive supercritical fluids and mountains are made of gemstones forged in eternal storms. We have witnessed stars fleeing their homes at unimaginable speeds and planets wandering the eternal dark, possibly cradling secret seas. Each of these 25 facts reveals a cosmos that operates on a scale and with a creativity that continually shatters our earthly expectations. These environments are not just hostile to life as we know it, they are actively antagonistic, places of crushing pressure, searing heat, absolute cold, and radiation that shreds molecules. Yet within that hostility lies a profound truth. These extremes are the universe's ultimate laboratories. They are the crucibles where matter is tested, transformed, and forged into new states. The physics that creates a pulsar's perfect spin or the chemistry that builds complex molecules on Titan's shores, these are the fundamental processes that shape reality itself. Our own planet, with its gentle climate and liquid water, is the rare, peaceful exception in a cosmos ruled by magnificent fury. So the next time you look up at the night sky, remember that each point of light could be hiding a world of unimaginable drama. Which of these facts left you the most awestruck? Let us know in the comments below. If this journey through cosmic extremes expanded your sense of wonder, please give this video a like and subscribe for more explorations into the universe's greatest mysteries. Keep looking up.